Hey everyone! Happy Women and Girls in STEM Day! Today I'm going to go through the first task in the NMR challenge. So, in this task, we are given a molecular formula, a proton NMR, and a 13C APT. So, the thing that we can work out from the molecular formula is how many double bond equivalents or how many degrees of unsaturation the compound has. And the 13C NMR and especially the APT can tell us how many protons are attached to a particular carbon. And the 1H NMR will tell us the environment, the chemical environment of each proton, and the 13C NMR will of course tell us the different environments each 13C is in. So without further ado, let's begin from the molecular formula. That's always a good starting point because that tells you what kind of functional groups are possible. Because like if you don't have any degrees of unsaturation, you know that you can't have a carbonyl group, you can't have an alkene, because those require degrees of unsaturation. I have covered degrees of unsaturation in my inorganic video series, so if you want to take a closer look at that, you can check out my previous videos. So here, to calculate the degrees of unsaturation, we first take the number of carbon, multiply it by 2, then plus 2. This is the number of hydrogen atoms if there are no degrees of unsaturation. Now we subtract the number of hydrogen atom we have here. So if you have a formula that contains a halogen, then that also counts as a hydrogen equivalent. So yeah, I mentioned these rules in my previous video, so you can check it out. And oxygen doesn't go inside this calculation, so the thing we have to do is to divide by 2 now, because with each degree of unsaturation that you add, you remove 2 protons. So with this, we get 1. So we know that this compound contains either a ring or a double bond. Now let's take a very quick look at the proton and 13C NMR. So here, we notice that we have a particularly highly shifted hydrogen, and we have something in a carbonyl region in a 13C NMR. So here 171.2, this suggests an ester. But even if you do not know that, we know that this is so highly shifted that it must be next to a carbonyl group. So we can just draw the carbonyl group first. And then you can check out the integrations of the protons. So you have 2, 3, 3. And for the 3, it is highly suggestive of a methyl group. While for the 2 and 3 combination, in fact, it is this 2 and this 3, it is very suggestive of an ethyl group. So with that, keeping that in mind, we notice that the 3 protons here are near 2.0, so that's indicative of protons next to a carbonyl group, and that is consistent with our previous deduction that there's a carbonyl group present, so we can just draw that in first. So these 3 protons are accounted for. Then we can see even if we do not know that this 171.2 suggests an ester, we can see that the splitting pattern for this is a Q, and this is a T. And a Q means that these 2 protons, they are splitted by 3 other protons, and this T means it's splitted by another 2 protons. So we know that these 2 are splitted by each other. So this is an ethyl group with no oxygen in between. So we can just draw in the ester group, and then we can draw our ethyl group. So to make this even clearer, the reason why this is not possible is because then the protons at these two carbon positions will be too far apart to couple, so it will not produce a splitting pattern that is found here. Okay, now we know what our correct compound is. Let's make sense of the spectrum. Let me just clear this up a little bit. So we have our spectrum here. And I mentioned that these are called integrations. So they are the ratios of protons in each chemical environment. So this axis here is called the chemical shift. So the more deshielded a proton is, meaning the less electron rich it is, then it is going to go higher or towards the left of the axis. The same goes for the 13C NMR. So anything that is below this region roughly are sp3 protons usually, and anything above that are sp2. So this is just a general rule of thumb. And then another thing that is quite important is the splitting patterns. So without going into the details of splitting constant and everything else, just know that when you have 4 peaks that belong to this single signal, that means that these two protons are split by three other protons. And when you have three peaks in a single signal, that means these 3 protons are split by 2 other protons. And when I say splitting can only occur when the protons are quite close to each other. So usually they are 4 bonds away. Of course there are exceptions, but usually there are 3 or even 4 bonds away, but there are exceptions, but those are usually present in aromatic systems. So this is an unsplitted signal, so that's what we call a singlet. And this is what we call a quartet, well, this is what we call a triplet. So I'll cover all these in another video. And let's now briefly look at the 13C NMR. So I mentioned that the 13C APT is quite useful because it tells us how many, or rather whether there are an odd or even number of protons attached to a particular carbon. So 13C NMRs are usually proton decoupled. That means that we have decoupled the interactions between 13C and 1H proton and 1H nuclei, so they do not mess up the entire spectrum. So 13C APT, so we know that because there are so few 13C nuclei around, they don't really couple with each other that much, or at least you don't really observe them on the spectrum. So the 13C APT, back to why APT in particular is useful, and the odd and even number of protons present. We can first take a look at the solvent peak. So this is CdCl3, and it is a 1:1:1. Like the height is in 1:1:1 ratio, but we're not going to go into that. Just know that when you see 3 peaks of the same height inside the 13C NMR, it's usually CdCl3. So CdCl3 has 0 hydrogen attached to the carbon. So this looks like OH, but it is 0H. It has 0 protons. So all the signals, or all the carbons with an even number of protons are going to point up, while all the signals with odd numbers of proton are going to point down. So 0 is even, right? So even will point up. So if you see the CDCl3 peak appear like this, then that means this side is even and this side is odd. So just always check for the CDCl3 peak. So let's see if this is consistent with our deduction. So this peak, we know it corresponds to this carbon, so it is attached to 0 proton, so it is on the same side as CDCl3. So that verifies this further. And then we have this. So this is this carbon, so it's attached to 2 hydrogens, and that is also an even number. And that's why it also points up. And you can see the further away we get from the carbonyl group, the lower the shift has become. This is because the carbonyl group is electron withdrawing. And of course, this is more deshielded than this is, the carbon, because this is next to an oxygen, like this is next to an oxygen, while this is next to a carbon. Okay, now both of these methyl group carbons are attached to 3 hydrogens, and that's why both of their signals will point down. Okay, now looking back at the 1H proton NMR, this is probably a solvent peak. We don't care about it because it's not labeled. Also, usually you can find the table of reference for the solvents. Oh yeah, they give you the solvents here, so you can always check back the table of reference to find its shift. And then we notice that this one, which corresponds to the 3 protons attached to this carbon, it has a higher shift than these 3 protons because it is closer to an electron withdrawing group, and these 2 protons are very, very deshielded for sp3 protons, because it is right next to an oxygen and right next to an ester group some more, so it is they are very deshielded. So yeah, that's about all I can say for these spectra, and I hope you learned something from this video, and I'll see you in the next one. Bye!